So, you on mute.
এই এটাকে তোমার ওই ওই করে দাও না, ওই আবার করে দেবে ওই ওই অর্গানাইজার নাকি অর্গানাইজার নাকি আছে ওটা করে দাও।
ঠিক আছে, আমি তো অর্গানাইজার।
না না, ওই আমাকে অর্গানাইজার করে দেবে।
তুমি তো আর নেই, আমি তো আছি।
না, তুমি যে ওই অন্য সময় করে দিতে আমাকে।
না, এখন তো আমি তোমার হয়ে লগ ইন করে আছি।
না তাতে, ও আচ্ছা, তা তুমি তো অর্গানাইজার।
হ্যাঁ,
না ওই ওরা মিউট টিউট করে দেবে।
এখন এবার ক্লিক করে নেবো।
শেয়ারটা
হ্যাঁ, ঠিক আছে। Can you hear? Just এবার ঠিক আছে।
শেয়ার করা আছে ওদের, শেয়ার করা আছে ওদের। হ্যাঁ, yeah, okay. So yeah, so what you saw is that when you considered the এই একটা এই পবিত্র এই ফ্যানটা চলো, একটা ফ্যান চলো, তোর ওই ওই ওইগুলো যেগুলো দরকার নেই ওগুলো বন্ধ করে। হ্যাঁ এই ব্যাস, থ্যাংকস। না ও ব্যাস ঠিক আছে, ওইটা ওইটা দরকার নেই, ওটা মানে তোমার যেটা দরকার শুধু। Okay, so what you saw is that when we were first we looked at machine minimization, which is done in the same way as we did for incompletely specified finite state machines. Then we saw the need for state assignment, and there we saw that the state assignment is indeed a critical matter. So an assignment for these states is shown over here. S00 is coded as 00, S1 is coded as 01, S3 is coded as 10, and S2 is coded as 11. So here what happens is when you try to make this transition, there are two bit changes involved. So 01 changes to 10. So that, and there, so what happens is that when you try, when the actual transition happens, it may not happen, it will usually not happen directly. So it could change from 01 to 00. And well, here we saw that once it changes to 00 for these inputs, 00 and 11, we do have transitions to S3. So even if it momentarily moves to this state, it will still come here. But that doesn't happen here. Because here, when it comes to this state, you find that for 1, 1, this one is a stable state. So it may not come here. It may remain stuck over here. So that's a problem. So this situation is called a race. So you have anyway, we have defined race below. So when a transition A to B involves multiple bit changes, the actual transition can occur through several states. So so this situation is called a race. Okay. Now you have a non-critical race when so here we saw that the race is non-critical in the earlier one, because well, you have the transition from here to here, but even if you come this way, you still come here. So that's a non-critical race. It doesn't matter whether you come this way or this way, but it becomes critical. The other one is critical. So if you come this way, what you found is that it you don't have the desired outcome. So when race paths are finite but terminate in a distinct state. Now, let us see something more. Okay, so is this much okay with you? What has been told? Have you understood the problem of this transition from S1 to S3? Yeah, everyone. Okay. So let us look at this. So why don't you do this yourself? S0. You look at the situation here, S0. So when you get 1, 1, why don't you investigate what happens when you get 1, 1 in S0? Yeah. In S0, what happens when you get 1, 1? Why don't you check that? Why don't you do an analysis? Just look at this and do it in your notebooks. And then you can show me. So you're in state S0, you get 1, 1. Then what do you think can happen? Just do it in your notebooks and show me. You're in S0 and you have got the input 1, 1. So, first of all, tell me ideal condition. 0, 0 changes to 0, 1. So your inputs are 1, 1. So 0, 0 changes to 0, 1. So you go to x1. Now you have already seen in the earlier discussion from 0, 1 on 1, 1 it is supposed to change to x3. But again, that's a multiple bit change. So it would just change back to 0, 0. Alright, so again, so that cycle on. Alright, so here you have cycle as well. So there are problems. I mean, there is no guarantee that it will go to S2. It will get stuck in the cycle. So this is a situation where it doesn't even reach a stable state. So these are the problems with races and cycles. Okay? So have you understood these problems? So so this encoding is problematic. All right. Let us consider another encoding. Here you have a different encoding. So why don't you know how to Yeah, so those of you who are online, in case you missed out what was said, so just want to repeat briefly. So uh, in the previous diagram, what you saw is that when you're in S0, if you get the input 1, 1, you can get stuck in this cycle. Okay, you can get the input is 1, 1. So for the input 1, 1, you find that there is a cycle between S0 and S1. It is possible for the machine to get stuck in that cycle. So we are just evaluating another state assignment. Here you will see that there is a slight difference to the earlier assignment. And now you are asked to analyze the transitions resulting from this assignment. So what will be the objective of your analysis? You have been asked to, what will be the objective of your analysis? Yeah, so are there any critical races? That is what you want to find out. If there are no critical races, then this assignment should be okay. So check whether this assignment can lead to any critical races. Okay. Yeah, so can you carry out an analysis and see whether you have any critical races? So when can you have critical races? When can you have critical races? No. That is a kind of critical race. But when can you have critical races? When you have transitions between states whose encodings differ by more than one bit. All right. So first of all, you got to look for transitions which involve states encoded such that the change is more than one bit. So can you identify such transitions? S1 to S3. Other transitions are okay. So you don't expect critical races in those transitions. So you only got to analyze S1 to S3. So analyze that. Huh? Not critical. Everyone is convinced. Are you convinced that so there is a race. There is a race, but the race is not critical. All right? There is a race, but the race is not critical. So this state assignment is okay. All right. All right. So what is so do you have any observation? I mean, between this state assignment and the earlier state assignment? Huh? Yes. S1 to S2. No, just a minute. S1 to S2. On which input? On 1, 1. Yeah, so on 1, 1, yeah, so that's a critical race, right? So on 1, 1, it is supposed to go to S3. So that is the critical race. That is a non-critical race. That is a non-critical race, which comes up when you have the transition from S2 to S3. All right? That's the non-critical race. Sorry, S1 to S3. From S1 to S3. That's the non-critical race. When you consider the transition from S1 to S3. All right? So between the two assignments, huh? Does it? No, see, S1 you want to go to S3 on 1, 1. So suppose you go to S2, so on 1, 1, oh yeah. So you do have a cycle here. You do have a cycle here. Sorry. So this is also problematic. This is also problematic. All right. So here also you have a problem. All right. So the question is, so what is your so from this by considering these two assignments, do you uh, do you have any kind of insight? So what I mean, a fairly obvious insight is that if you could have a state assignment where the uh, the state encodings are adjacent when you have a transition, uh, there you could or basically you have to engineer the transitions. You need to engineer the transitions to avoid the cycles. So let us just see how that could be done. So here, as you can see, it's a bit problematic. It's a bit problematic. Let us try to look at this. So I think this is that same diagram. This is that same diagram. We are we are looking at, we have just drawn it a little differently now. We have drawn this diagram a little differently. Okay. So, so what we have done is we have, so this you can think of as a hypercube. Okay, it's a hypercube. It's a two-dimensional hypercube. Okay, so here, if you have any transition along a diagonal, some kind of diagonal, then that's uh, the that could give rise, that will give rise to races. All right. So if you have any this, so these are transitions between adjacent states. So these are okay, but you have this problematic situation here. So suppose we uh, so basically, you don't have enough nodes. So what if we did increase the number of nodes? Okay, so we have just we have added another bit to the state encoding. All right, and now since you have added another bit, you are now considering a three-dimensional hypercube. Okay, you are considering a three-dimensional hypercube. Now, what you're seeing is that these the original nodes are shown unfilled. Now, to avoid those those problematic transitions, we are uh, we, uh, we, we are routing some of the transitions through these other nodes. Okay, through this intermediate nodes. Okay, and and we are defining the transitions from the intermediate nodes so that those transitions will basically uh, correspond to the transitions of the original machine. All right, so what you can see is that through this method you are able to avoid those critical races. You do have races, but those races are no longer critical. All right. So this is a way to, so what you can do is you can basically try to embed, your state transition diagram into a hypercube, and if necessary you can route some of the transitions through these extra nodes that you may have in the hypercube so that you no longer have critical races. All right. So, so this is what is I mean. So you can see that in for this machine, you don't have any critical races. All right. So, I mean, at the moment, this is all. So, Povitra, Povitra लेकिन नजर से बोल लो। ऐसे बोल दो, ऐसा लोग शुरू कर दो। कल आवाज है।
Yeah. No, it's not there. up to minimization. So Boolean lattice, Boolean algebra, then this. Right, that's the last one. Okay, so can you hear me? Yeah, I think you can hear me. So one thing will continue is that there is a notion of something called an hazard. So the idea is like this. If you look at the response of the circuit, a change in input. So sometimes there are undesirable elements. So there can be. So what happens actually is when you change an input, the output does not immediately change. So there are two kind of delay. One is a propagation delay. One is a propagation delay. The other is something called a rise time. The other is something called a rise time. So what happens in rise time? That you don't have a step like a function. You have a linear, you have a ramp kind of function. Going from one ramp to the other. So because of this delay, what happens is that when you change a monotonic, you change the input monotonically. That means you get a single change from 0 to 1 or 1 to 0, or maybe 0 to 0 or 1 to 1. So there is the flip that it doesn't go from 0 to 1 and comes back from 1 to 0. Then what happens is that usually you require in the fundamental mode of operation. Fundamental mode of operation meaning the input changes only once till the circuit stabilizes. There are not multiple changes in input, and after the circuit stabilizes, then the subsequent changes happen. So if we look at monotonic changes, and again the changes can be two type of changes. One is a single input change, that means only one bit changes, and the other is a multi-input change. There is multiple bits may transition. So what may happen, what we call as a glitch or a hazard. I mean, hazard is a property which leads to a glitch. Is that for monotonic input transition, there may be non-monotonic output transition. So the input, there is only one transition from 0 to 1, 1 to 0. But in the output, because of the nature of the combinatorial circuit, a monotonic change in input should produce a monotonic change in output. Whereas that does not happen due to the delays in the circuit, due to the delays and the underlying logic of the circuit. And this usually happens, as you told me, due to differential delays in each path of the circuit. And these are undesirable in the sense that even though these are erroneous transitions, erroneous values, the other parts of the circuit may consider this as valid transitions and may take a corresponding action, which is not correct. Second is this kind of transitions take up energy, take up power, which is very critical. Third is this may slow down the response time. You cannot increase the clock speed if you have such delays beyond a limit. Okay, so we are interested in three types of hazards. Again, hazards are again there are two reasons, two causes of hazard. One is called a logic hazard, which is because of the implementation, because of the circuit, because of the paths in the circuit, there are this kind of glitches. And second is a function hazard, where it is inbuilt in the function. The function itself will produce it, which are difficult to remove. But logic hazards you can easily remove. So we are looking at three kind of hazards. One is something called a static zero hazard, which means the output signal should have been static at 0, but there is a momentary value of 1, momentary value of 1. And the other one is the static 1 hazard, where it should be at 1, but there is a momentary. Note that all these glitches, everything, these are only momentary changes. These are, if you allow a lot of time, these changes would not be visible. It's only momentary. It is not forever. But the problem is that these momentary changes may affect other parts of the circuit. And then you have the dynamic hazard, where the output should have been a transition from 0 to 1, a step kind of transition, 0 to 1 or 1 to 0. But instead of one single transition, you can have multiple transitions. Like there is a 0 to 1, and then again 1 to 0, and then again 0 to 1. You have multiple transitions. And these have to be avoided. So let us see an example. Let us see an example of a static 1 hazard. That means the output should be at 1, but there is a momentarily glitch at okay, so let us look at the circuit. You can see, let us look at the function a b prime plus bc. So here is an implementation. The implementation is like this. You have A and C, and you have B. One goes through a NOT gate, and other directly goes as input to two AND gates. And the output of the AND gates are fed to an OR gate. So this is the straightforward realization of this circuit. And if you look at the Carnot map, if you look at the min terms in the Carnot map, you see that these are the min terms that are there in the Carnot map for this. And we want a single input change, the following manner. So you have 3 bits as input, A, B, and C, out of which A and C stays at 1. Out of which A and C always stays at 1. And B has a 1 to 0 transition. So B falls from, B is initial. So initially the input bit ABC is 1, 1, 1. And then there is a change to 1, 0, 1. There is a change to 1, 0, 1. So you can easily check that in the Carnot map, which means that there is a, you look at these two red blocks. So there is a, from the lower block 1, 1, 1, there is a transition to the next higher, which is 1, 1, 1, 0, 1. Okay, and let's assume that each of the gates have the same delay, which is 10 nanoseconds. Okay, and we'll see that this circuit will have a static 1 hazard. So let's see. In order to explain, what we need is called a timing diagram. So this timing diagram is slightly wrong in the sense that you see sharp edges, you see square edges. Actually, there will be a ramp kind of structure. There will be a rise time. There will be a linear ramp kind of structure. Okay, so now let's see what happens. So A and C are always at 1. I have not plotted A and C. Let's plot B. Okay, let's plot B, and let's see what happens to D and E. What happens to D and E? Okay, so B is first 10 nanoseconds. There is no change in B. Since there is no change in B, D and E, D is at 0. Okay, B is at 1, A is at 1. So D is an AND gate. So D is at 0, first 10 nanoseconds. In fact, first 20 nanoseconds. E is at 1. You can check if B is at 1. And then F is also at 1. Because both B and D and E are at 1, F is also at 1. Now what happens? Now at the 20th nanosecond, B drops to 0. B drops to 0. Now let's see what happens. So as B drops to 0, one of the input of D should immediately transition to 1 because there is a NOT gate. But that will not happen. NOT gate will have a 10 nanosecond delay. So the input to change for D, moment B makes a change, it will wait for 10 nanoseconds before the output of the NOT gate changes. Just to wait. Only after that it will change. Okay, and then now D also, this NAND gate also has a delay. So that D will have a further delay of another 10 nanoseconds. So this is the NOT gate. This is the AND gate. Will have a further delay. And after that, okay. So all right. Now let's see what happens. AND gate like NOT gate is. NOT gate is not there. It will only have the NAND gate is. So that's it. NAND screen is there on this side, and after that you. Right. So now let's look at F. So at this point, we can look at F. You can do this is 0. This is 0. But the thing is that F immediately doesn't become 0. Doesn't it? Because of all. So F becomes 0 here. F becomes 0 here. And then you look at the next enhancement. Now E is 1. B is 1. B is 0. B is 0. B is 1. B is 0. So now B becomes 0. B is 1. B is 0. But B will not become 0. So then the yes, so from that will become identical. It will continue. And from 15 and a second onward, now it is over. Now they are in the complete. So the net effect is that it should have been, unless this differential delay is there in each part, it should be always 1. It should be always static 1. Let's start with static 1. Because of this delay, that's the squeeze of 10 nanosecond. That's the squeeze of 10 nanosecond. Right. So this should be applied. This should be applied. And we'll see maybe today not. Next class we'll see how to avoid, how to detect if such a glitch will happen, and how to avoid such glitches. Right. So similar analysis you can make for studying 0 results and that. And this is as far as removing the glitches go, there are several things. One simple thing is that you wait enough. You wait for this next over and then look at the signal. Okay, you wait for some time and then look at the signal. Okay, then this glitch has no effect. It doesn't affect other parts of the signal. Okay, but that how that can be done? You can use a clock whose cycle is much longer than these delay cycles. But the length of the path, total path, is a clock cycle larger than. Then you can easily wait time. But that will slow down the system. So there are other ways. So what you do, you include redundant gates to remove the delays. We'll do that in the next class. Thank you. Thank you. I think now we are done.